Okay, hello everybody. Today the video lesson is going to be to determine the potential due to an infinite line of charge. Okay, and we're going to be using a path integral to determine that potential, and we're also going to be using the electric field result that we had previously determined for an infinite line of charge. So let's start off by sketching a line of charge. Of course, I can't make it infinitely long, but I can always cheat and say it's going to go up to plus infinity, minus infinity. We can imagine positive charge being spread out. We're going to assume that this is a uniform density of so many coulombs per meter, so that would be lambda, the lambda type of density. And what we're going to try to do is we're going to try to figure out the potential difference between 2 points A and B. So our goal is to derive the potential difference between those 2 points, which are outside of the wire. So one of the parameters, the only parameter that we're going to really need here is going to be a radius parameter. The radius is going to extend from the center of the wire, and it can go to any position that you want. So r, lowercase r, is going to be the parameter, and we are going to want to do a path integral on this. So we're going to use this approach where the change in potential from A to B is going to be equal to the path integral of the electric field dotted into the path that r would follow. Okay. Now, one of the things that we have to recognize right away is that the electric field lines created by this wire are going to be radially directed. Okay, so this is kind of like the analogy to the car washing brushes that we talked about, where the electric field lines come out like as radiuses. Okay, and the nice thing about this, this feature of the electric field is that the electric field perfectly lines up with the radius as the radius extends. So when we take the path integral and we take E dot dr, we don't need to worry about the angle between those vectors because the angle between them is always going to be 0 degrees. So that's actually a nice feature, that angle is 0. Okay, so that's good. The other thing that's nice about this is we know that the electric field strength around an infinite wire is given by a nice formula that we derived earlier using Gauss's law, and that formula is 2k lambda over r. So not only do we know that the electric field and the radius are parallel to each other, but we also have an expression for the electric field that we can plug in. So this integral actually is a pretty simple one. It's going to become that. So the electric field magnitude expression just plugs right in. Okay, so now let's rewrite that. Let's factor out 2k lambda. Those are constants. And then instead of writing 1 over r, I'm going to write r to the negative 1. And then we're going to have to integrate. This particular integral is a special one, because when you integrate a variable to the negative 1 power, you end up getting a natural log function. So this is sort of a special one, and it pops up a lot in physics, so make sure that you recognize it. So the solution to this integral would be 2k lambda times the natural log of r evaluated from A to B. Okay. Let's simplify that a little bit, and we'll say this is 2k lambda times the natural log of RB minus the natural log of RA. And we have a difference of logs here. So that can just be written as the natural log of the quotient of RB divided by RA. And so that would be our result for the difference in potential between those 2 points. Okay. Now, this function has a shape that would be something like this. A natural log function is going to be something which kind of goes up to positive infinity here, and then it's going to swoop down, but when it swoops down it doesn't have any asymptote, so it's really going to go down to negative infinity. And we're going to see in just a minute that that's going to be a little bit of a problem, because it's going to be very difficult for us to define that as zero, a potential of zero. There's no way, in fact, that you can say that the potential would be equal to zero out here. That's not going to work for us. So the next thing that we're going to do is we're going to take this answer, this expression, and we're going to try to find a workaround so that we can at least define the zero potential to be somewhere, so that we can do something with it. Okay. So I'm going to copy that expression down again. Okay, and we have that. And let me show you what I mean by this. You know, if you take, for example, let's say that we want to make try making the potential equal to 0 when RB is equal to infinity. Okay, so if you tried that, you would end up with something like natural log of infinity over RA. And that just becomes infinity. And so it's not gonna allow us to do what we want. We won't be able to define the potential to be zero when you're infinitely far away from the wire. Okay, because the potential is just going to keep on changing no matter what. So we have to do something else with this. And what we can do with this is we can try a solution here. The solution is going to be to define the potential to be zero at some kind of arbitrary specific value of the radius vector, and we're going to call that R naught. Okay, so at R naught, when RB is equal to R naught, we're going to just say that the potential is equal to 0, and we're just going to kind of set it equal to 0 there. And R naught is not infinity, by the way. It's going to be a point that's closer to the wire. Okay, so that is going to allow us to change our expression here. We had delta VAB is equal to that, where we're going to basically say that the potential at B becomes 0 at this particular value. So I'll circle that, right? So that's like a constant. Okay, it's a constant. It's not infinity, and it's going to be some point that we have to decide on. And you'll see there's a reason for setting the value of this constant in just a couple minutes. Okay. So this is our expression. I'm going to simplify things a little bit here and get rid of the A, So from now on, we can just talk about the potential. At some particular radius value, r. So the variable here is r, and as r changes, the potential is going to change according to this result. So what would this look like if you graphed it? Because I think graphing it is going to help to clarify things for us. So if we graph this, and you graph the potential as a function of distance from the wire, what you're going to have is a function which basically swoops down, and at some point it's going to cross this axis. This is r0. Okay, and hopefully you can see that this function, that's the crossing point. So the crossing point at r0 is going to be where the potential is equal to 0. And so that's kind of the point, like a location that you would set in a problem. You would say, okay, I'm going to decide to make r0 so many centimeters, and my potential is 0 at that point. The idea with this is that we're anticipating that we're going to be dealing with cylinders where r0 is going to be the cylinder radius. So if you've been wondering about all this business of r0 and it seems kind of artificial, well, in just a minute you'll see, as soon as you start to talk about an actual cylinder, you're going to use the radius of the cylinder is going to be this point that you set the potential equal to 0 at. Okay. So that's it. All right. So to kind of summarize this, we have a logarithmic function for the potential. We have not yet seen a logarithmic potential until this example. The problem with a logarithm is that it doesn't have an asymptote, and so we have to make this definition of a crossing point is where the potential is equal to 0. So let's finish up here and apply this to a solid conducting cylinder. And that, I think, will help it to be a little more concrete for understanding. So my cylinder is now going to be something like this. It's going to have a radius, r, and it's going to have some charge, of course, that's spread out on it. Okay. We could make it infinitely long, sure. So plus infinity, minus infinity. And the charge is uniform. Okay. And one of the questions you might say, well, is the charge spread out inside of the cylinder, or is the charge spread out on the surface? And my reminder to you would be that this is a conducting cylinder, and so we should be knowing that the charge is going to go to the surface of the cylinder. So really the charge density in this case would be a sigma, because the charge is all going to go to the surface of the cylinder. Okay. All right, so let's look at the what we have in here. So let's look at inside the cylinder. So let's say that you look at radiuses which are less than the radius of the cylinder itself. Okay, so this is inside. And we know from Gauss's law that E is equal to 0 since all of the charge is on the surface. So there's no electric field on the inside whatsoever. Okay. For that reason, since the electric field is 0, we know that the potential is going to be constant. Okay. The potential is going to be, whoops, I didn't mean to say 0, I meant to say constant. Not necessarily 0. And to think about that, you can remember that the electric field is always the derivative of the potential with respect to position. So if the electric field is equal to 0, that means that the electric potential is not changing at all inside of this particular cylinder. Okay, so that's the reason why the potential is constant. So that's important. So the potential is not necessarily 0. It could be anything, but it can't be changing, is the idea. Okay. Now we are going to set V is equal to 0 inside, okay, and on the surface. So we have the freedom to actually decide on a value for the electric potential, and we're going to say that the potential is equal to 0 at that point. And so this is the connection to the previous derivation. Remember, we said that R0 was the place where the potential could be equal to 0. So in this case, we're saying R0 is equal to R, and that's where V is equal to 0. And then we can say, well, use that and look at outside the cylinder, and our expression would be the expression that we derived just in the first part of this lesson. It's going to be equal to 2k lambda as the natural log of the cylinder radius divided by the variable radius. So this is the radius of the cylinder here, and this is the variable radius that's down here. So what this is going to look like is the following. We'll make the graphs over on the side. Graphs are really important here. We could graph the electrical field versus R. Okay, we can also graph the electric potential versus R. I made a mistake here. I wanted to give myself a little more room. Okay, like so. So let's take a look at what we know. We're going to put the cylinder radius on our graph, on both graphs. We can add it there. And we know for the electric field that inside the cylinder, the electric field is equal to 0. Okay. And then when you jump up to, when you hit the radius of the cylinder, what's going to happen is the electric field is going to jump up, and it is then going to drop off, given by the function E is equal to 2k lambda over R. So basically that's the same formula that we derive for an infinite line. And the electric field outside is going to be given by that same function. That's by Gauss's law. It's something that we showed in the last unit with Gauss's law. So if you have a charged cylinder, the outside of the cylinder basically is looking like a charged line. Now the potential is the thing that's new, and from what we said over here on the right, the potential itself is going to be 0 by our definition up until you reach the radius of the cylinder itself. When you're at the radius of the cylinder, it's still 0, so I'm going to put a dot there. But from that point forward, you are going to be following that logarithmic curve, which is going to take you down like this. Okay, and that's the logarithm curve, and so that's proportional to the natural log of R over R. And yes, that's negative. You can try that on your calculators. This will put you into the fourth quadrant because you're taking a number and dividing it by something which is bigger than that number. So this is the log of a fraction. Okay, so the ln of a fraction is a negative number. But what's interesting about this is that the potential basically gets more and more negative the further away from this positive cylinder that you get. It never approaches 0, so there's no asymptote here. And so you can't really talk about defining, V is equal to 0 at infinity, because that just doesn't work. Okay, so the math of this is kind of interesting. It kind of makes sense from the point of view of if you put a small positive charge really far away, basically that charge, the further away you put it, the more and more potential energy is going to be kind of stored in it in a sense, because when you release it, it's going to just come back with that much more kinetic energy. So so that's kind of another way to think about it from the energy point of view. Okay. All right. So to summarize, what did we do? We in the first part of this lesson, we derived an expression for the electric potential as a function of distance from an infinite wire. We decided that we will set the potential equal to 0 at some fixed value of the radius. And then we looked at kind of the practical case of what to do when you have a solid conducting cylinder. How do you find the potential around it? And the answer is you basically set the potential equal to 0 within the cylinder and on its surface. And then beyond that point, you can see the logarithmic result would apply to it. Okay? All right, so we'll talk some more tomorrow.